Here in this question, we're told that there are two blocks and we're given their masses, 4 kilograms and 6 kilograms. They're lying on a smooth horizontal surface, so there's going to be no friction, and they're connected by a light, inextensible string. Two collinear forces of magnitude F and 30 newtons act on each of the blocks. Collinear just lets us know that they're moving in the same line, in the same plane. This is all shown to us in the diagram, and we're told that the system has constant acceleration of magnitude 2 meters per second squared. Determine the possible values of F, and in each case, the corresponding value of the tension in the string. Okay, a couple of things to notice. Firstly, we're told to look for values, multiple values. We know this system could be moving either to the right or to the left, and there are two cases in which this will happen. If F is a small value, 30 is going to be the driving force, and 30 is going to make us move off towards the right-hand side. If F, however, is quite a large value, it will overcome the 30 newtons, and this system is going to be moving towards the left. So I'm just going to consider both of them and find tension and this unknown force in both instances. So let's start with the instance where we have a low value of F, a small value of F. Okay, I'm just going to get a diagram so I can see exactly what's happening. All of the forces that we were given before, we need to know to put these internal tensions on for ourselves. So tension moving away from block A and tension moving away from block B. This is the situation that we have. The direction of movement this time round for this low value of F, like I said, is off towards the right. And the acceleration is a value of 2 in that positive direction, with the right hand side being our positive direction. So F equals ma, and we'll just decide where we're going to focus to start with. Let's focus on particle B. This has the 30 newtons, the unknown tension, and a mass of 6. So substituting those in, the force here, the left-hand side should be the resultant force. So 30 is in the positive direction, T1, tension 1, is in the negative direction. So 30 minus T1 equals 6 times the acceleration, it's 12, and with some quick rearranging, we get that T1 must equal 18 newtons. Okay, now that we know the tension, we can focus on particle A, and we can find out this unknown force F. So T1 minus F is going to equal the new mass times acceleration, it's 4 times 2. That leaves us with 18 minus F equals 8, so F must equal 10 newtons. Okay, so this is one case, like I said, where the force is quite low. It's not enough to change the direction that this system is moving in. So if we had a higher value of F, a large value of F, that would be enough for us to be moving towards the left. Let's just get a diagram to represent what happens in that case. So the particles are still there. I do have tension in between them. I'm going to label these tensions differently this time. I've used T1 on purpose, so this time I'll use the subscript of 2 to get T2. The direction of movement is towards the left, but the acceleration is still 2. My positive direction from now on, for this part of the question, is going to be to the left. So, Newton's second law again. We'll start on particle B. So the tension this time, T2 minus 30, is going to equal 6 times 2. So T2 minus 30 equals 12. T2 must equal 42. So the tension now is 42 newtons. Using that tension and focusing on particle A, F, the unknown force, minus T2 equals 4 times 2. T2 we know is 42. That added onto the 8 gets us an unknown force of 50 newtons. So, considering both of these cases, we found the tension and we found the unknown force.